So thank you for coming to our session. I realize that we probably have our room is a little too small. The overflow for everyone in the back there, the overflow is in the other room. A little slight misjudgment. Okay, so let's talk a little bit about what this talk is about. Windows Azure from the pulpit to the whiteboard. You might wonder why that is in the title. I feel like I'm at a pulpit right now. However, Wade and I'm Ryan Dunn. This is Wade.
Wade Wegner.
We were Windows Azure evangelists at Microsoft for quite some time. So my backstory is I joined the evangelism team in like 2008 or 2007 actually. And Windows Azure was released to PDC in 2008. It was called Red Dog. We didn't even have the Azure branding yet. Over the years, obviously, we get pretty familiar with the platform and some of the things we do, and this talk is really kind of the culmination of what's happened after we left Microsoft. So we took some of the best practices that we had always preached, and we put them into real implementations that actually were trying to make money and not just demos. So this talk, we're going to be talking a lot about kind of the lessons learned, some of the scenarios we ran into, and the things that really made it valuable for us, where the preaching ends and the actual implementation begins. Wade, why don't you give yourself an introduction? I know I did some of it for you, but I think it's valuable. He did even more than me.
So, my name is Wade Wegner. I actually joined a little after Ryan at Microsoft, but was focused on Windows Azure since 2008 as well. And left the team about a year ago, so I got to work with a lot of great folks. So as Ryan said, we're going to talk about some stuff that we've done since we've left Microsoft and some of the real services we built. Now,
you'll have to forgive us. We have to mention where we're at now and what we actually do. It's kind of a backstory of why we're discussing this. I'm going to let Wade go.
So we work at a company called Aditi. We're a services integrator, so we do a lot of consulting work on the Microsoft platform, focus a lot on Windows Azure. One of the things that we've done recently over the last year, particularly Ryan and I, is start building developer services that we offer to not only our customers, but we also make them available through the Windows Azure store. So we're going to talk about a couple of these services today. You can go ahead. And we've built these services for some of our customers. And if you go one more, one of the things that we do want to emphasize is, a lot of the work that we do is focused on Windows Azure and the cloud. And as part of that, we've been the Windows Azure Partner of the Year for the last 3 years. I'm not sure about this year, hopefully. So we do a lot of great work, joined by some colleagues here as well. So with that aside, we can go ahead and get into what we're going to talk about today.
Great. So we're going to cover 3 main things today, and we're probably going to spend a lot of time on the first part. How many of you have actively used Windows Azure or are actively using it? Great.
Excellent.
So this is good because you're going to find it probably more valuable. We're going to talk about DevOps from the perspective of a small startup, and as we operate internally in Aditi as a very small team as well, some of the things that we did in order to get this software shipped and the lessons that we learned. And finally, we'll briefly touch on kind of handling disaster and downtime, which will occur. So it's not an if, it just will occur. All right. So, quick backstory. Aditi purchased a company called Cumulux and integrated it into their fold as a consulting service. So when I was at Cumulux, we built this service called Azure Ops. It was a monitoring site for Windows Azure. And at the peak, we monitored right around 3,000 VMs. We did this at the time in all of the data centers that were available. We processed, ungodly amounts of data, just terabytes and terabytes of trace messages. We'd parse those trace messages, alert on them. We'd give you performance counters. We'd monitor it. You could set rules, alert me if my CPU is over 40% for an hour, that kind of thing. When we did that, we actually ran our entire system. Initially, we ran our system on 6 smalls, and that didn't work, and we'll talk about why it didn't work. But the end state deployment ended up being 2 smalls, 4 mediums for the core deployment, 2 mediums per data center that we had to geolocate, and 12 extra small instances. Extra small instances will end up being a savior. We'll find out why. We auto-scaled, and we did all these alerting on this entire infrastructure. Now, that's not to say we didn't scale. We had auto-scaling ourselves, so we ate our own dog food. So sometimes we'd scale up to 16 instances and then back down to 4. It just depended on what our customers were doing.
And so more recently, one of the services we built has been a scheduling service. We took a look at a lot of the projects that we had done in our cloud practice to try to distill down what some of the common use cases and services were that we could extract out of these custom implementations and then build them as a service. And so we actually, in January, started building the scheduling service. And we won't go too much into the story about onboarding into the Windows Azure store. That was actually from a talk yesterday that you might want to watch. But we actually, in the matter of about 2 weeks, took our service and actually got it into the Windows Azure store. So today, you can actually go into the management portal and go to add-ons and add the Aditi scheduling service. If you go to the next slide. So what this does is it's actually a service that does time-based job scheduling. So it does everything from simple web hooks, so you can do an HTTP GET, to an endpoint of your own on a regularly occurring basis. It also allows you to do post. You can modify the headers. You can post information along in the body. There's basic auth supported as well as no auth authentication. And there's even an SDK API available for it as a NuGet package. We've had about 500,000 job executions since we ended up bringing it into a free preview. Then actually just about 2 or 3 days ago, we went generally available with it and offered a bunch of paid plans. So this is the other service that we've built. And I think the reason we mentioned both of these is these form the foundation for much of what we're going to demonstrate and talk about today, which is the underlying architecture for how we can end up building these highly scalable services.
So I took a lot of the lessons learned from building Azure Ops and how we built that system to be responsive and to scale with that few small machines, managing to monitor 3,000 machines and pull in that data, do the crunching, do the alerting, and run all that together. And I'm going to talk about it. If you're familiar with the concept of CQRS, this slide might look a little bit familiar, but I'm going to talk about it in some detail here because we're going to keep touching on different concepts in this slide. So the general, kind of in a nutshell, is we're splitting our reads and our writes, right? In this diagram, the web and the client at the top is making queries, passing through a very thin data access layer into view data. And you'll see that this data is actually purpose-built, driven, static data. We're not making any joins to get this data. We're just simply serving it as fast as we can off of disk. So you can think of it like pre-cached data. The web client or the scheduling engine, whatever it is that's actually injecting the work to be consumed, is sending commands into our system. And we have an event bus. And I'll talk about this and show a little bit of the tooling that we use for this. But the event bus actually dispatches that command to a command handler. And the command handler will in turn consume data generated by events. So internally we have an event sourcing solution. We record what happened. An example is you register with us. We'll send a register user command with your details. We'll go down. We'll actually save it as user was registered. That event will get then raised back to the event bus and dispatched. And depending on who's listening to that event, it can cause all sorts of other behaviors in the system to occur. So one of it might be we'll build a view that has your profile now because we just registered you. Another will be that message will be picked up by our quota management system, and a new entry will be created giving you your initial quota. The next one will be our billing system listens for that event, picks it up, so on and so forth. So we can tie together previously disparate systems that kind of be little units of work, and the only thing we share is the fact that they listen for a specific type of message. And this has allowed us to build things in isolation, test them in isolation, and also have small teams working on them. If we tried it with other architectures, we actually found we weren't very good being able to share that much source. People were stepping on each other constantly. When we split it up, we actually can do this quite easily. So I'm going to talk a lot about some of the lessons we learned here in this architecture as well, but you have to understand this is the underpinning. So commands come in, events get emitted, and then based on the event bus dispatches it to what we call these denormalizers. And the denormalizers write views, static data, into our repository, and those views are served back relatively instantaneously to customers when they want that information. So the 4 components we'll talk about here is pushing your hard work to the queues, asynchronous. You have to learn to live with their stale data. We optimize for reads and working close to your data. I'll go into detail on each of these. Let's talk about optimize for reads. So the events that we talked about, they're raised from the commands and they're dispatched over the event bus. Our denormalizer picks it up and it actually creates a dynamic view. I'll show a demo of this. There's 2 types, I'll call them 2 types of views that we actually find in practice. One of them has static data. This is like your profile information. What's your address? What's your name? This kind of thing. And we found that storing the data on JSON files in blob storage has been a best practice for us. So we can view it, and we can literally read it out of blob storage as fast as you can serve the bytes over HTTP. I'll show an example of that. The next type we'll call queryable data. This is a little more interesting case. This is the case where you have, let's say, for Azure Ops, it was trace information. You wanted to know what the last hour of traces were on a certain day. Well, you really can't write that information into one file on disk. You can't pre-generate every possible combination of views. However, you can write a relatively disposable view that is indexed based on date time. So we would index in table storage based on date time, your trace information or your performance counters, which then when you asked us to query, what were my performance counters? We could very quickly and very efficiently retrieve exactly the information we needed. And we did this time and time again, every time the user had to put some input into the screen. So take a look at your UI. Break them down into tasks. If it's static data, you can create a static view. If it's queryable data where you're asking the user to input maybe a filter of some type, you're going to create a disposable view that takes into account that filter. And I'll show you an example of that. Working close to your data. So this is interesting. The bandwidth actually becomes limiting factors in Windows Azure. We didn't realize that this was going to be the case. It's one of those gotchas that kind of bit us. So initially we had deployed into a single data center, and we started pulling in diagnostics information. And we found out pretty quickly that that's not possible to pull someone a few gigabytes of a user's data across the WAN. Not only is it expensive for them and us, but also it takes a very long time. So we needed to really start to route our messages. We employed a message routing strategy, and I'll show you an example of that as well, where we could figure out where does this work really need to be done, and we'll send that command off to the data center that houses our worker roles in order to do that work. The bandwidth between the VM and the NIC can also be a limiting factor. I'll give an example of that, where you can actually completely consume the bandwidth on the NIC, and it can cause all sorts of interesting behaviors. So here's a real-life example that we found. We had a customer. They had 300 VMs deployed, hundreds of databases. They deployed with an error. So I don't know what it was. It was a SQL Azure connection error. And they had no retry back-off policy. It was in a tight loop, as fast as they possibly could. 300 instances were tracing out full stack traces on every operation on the site. The data that this actually created was just enormous. I mean, there was over 2 gigabytes per minute, as an example. So we found quickly that our NICs became saturated on the machines. The NICs became saturated. We couldn't read the data fast enough. Because our system was built with timeouts in mind, we got a timeout trying to read the data, which then allowed another instance to try doing the exact same work. So the first one couldn't finish reading before the next one started reading the exact same data. Our system noticed, of course, that the queues started getting high and went crazy auto-scaling. We had luckily capped it at 16 instances, but all of a sudden, one region shoots up to 16 instances. We're looking at our network performance counters, and every single one of them is absolutely just redlined. We're like, what is going on, right? Well, we figured out what it was, right? We took a look at the data, and it was like same error every single time, every second. And this taught us a very valuable lesson. Throttle, 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 throttle. When you're going to do anything, you have to look at the worst case scenario. You will find you will always have a customer who will inadvertently screw you over, especially in a multi-tenant setup, right? If there's a way to screw it up, they will find it. Like you will think, oh, there's no one who would ever do that. It will be done. You have to protect at every level. Protect at your reads, protect at your writes, protect at your timeouts, and be very, very cautious on your retry policies. So what I tell you now is probably not what the Windows Azure storage team will tell you, but I would disable all retry policies on the Windows Azure storage client. Put it on no retry. There's almost 0 cases where you want to retry those errors, right? If you got a DNS resolution failed, why would you want to retry it 4 times in order for it to stop? And that's what would happen. So we also found that customer would tell us their storage account is over here with their diagnostics information, then they'd go delete it. We'd go try to find it, and it would fail, obviously, with a DNS resolution. Well, we had a retry policy because we just left the default on. We weren't paying attention, apparently. It would take over 2 minutes for us to finally reject that command because it would retry 4 times with 30-second gaps. And then we were wondering why our queues keep getting bogged up. As soon as we disable those retry policies, everything chugged along. Be very cautious. All right, push your hard work to the queues. An example of this today is our scheduling service. So our scheduler has a repository of what data you have in it in terms of schedules. So you tell me, I want something every 1 minute. I want you to ping this every 1 minute. Well, that same engine doesn't actually do the work. We don't want it to bog down. We want this as lightweight as possible. It has to absolutely fire on the time we say it's going to fire. If we had a customer who had a slow responding web ping or something like that, theoretically, we did that work at the scheduler itself, it could slow down the scheduler to the point where we start to miss our next triggers. So what we did, we pushed everything to our queues. The scheduler fires, it says, go do this thing, whatever it is. And we have other back-end workers that can scale up as necessary, as many commands as necessary, in order to actually do the work the scheduler needs to be done. If it's push a message into a queue or ping a website or anything like that. Next, prioritize your queues. This is around the message routing. So imagine, if you will, you have a website that the user needs to register. In the same, you push a command into a queue that says register user. Now, you have only one queue, right? You only need a queue. One queue is processing all the commands in your system. Then you decide to use that queue to actually do, let's say, some big data crunching. So you can have these relatively lightweight messages, register user, being stacked on top of crunch a ton of data. And guess which one processes faster? Right? And your user experience suffers completely because it's waiting for the view to get updated and you didn't prioritize it. So what you can do is you can route the messages to different queues. If it's a user command coming from the UI, VIP queue. If it's a command coming from a scheduled task that needs to be done, and you can be a little more lenient on when it has to be done, push it to a lower level queue. If it's a queue that tends to have work that's very high latency, push it to yet another queue. We ended up with 20 different queues, depending on the type of work we're doing. The scheduler has different queues as well, in order to prioritize how fast should the work be done. When this is all done, your front end is essentially doing nothing. It's just going to send commands, and it's going to read JSON requests. We rarely, if ever, have to scale our web tier. The only thing we ever have to scale is our back end that's actually crunching this work. So another example around this prioritization. I give you a true life, this is what happened. Our auto-scale system would periodically kick on, and 4 instances would spin up. And we had some rules in there. So if this queue goes over a certain amount for this long, add some more instances to help bleed the queue. So we kept doing this, and then like 2 hours would pass, and we would bleed back down the instances because the rule wouldn't be met, and we'd keep dropping them away. But it was completely cyclical. If we looked at the graph, our instance count was like this, and then like this, just kept going. We had no idea why this was happening. We thought, well, what is cyclical in our system that could possibly cause this to occur? So we actually instrumented the system. We added custom performance counters that would, before we processed the command, would inspect what it was and would increment a count. And then it would also give us a time of execution. And here's what we found. We had to call the Service Management API a lot. And the Service Management API had an average of about 60 seconds in order to get all the data we wanted. And it would run as long as 240 seconds in some cases. Some people had a lot of deployments. Some of their deployments had an amazing amount of data in their configuration system. And so this took a very long time. Well, we fixed it. Here's what we did. This is why we brought in the 12 extra small instances. We pushed all of those commands that use the Service Management API to their own queue. We rewrote the system so that our main workers who need to do data crunching never looked at that queue, and we put 12 extra small workers on it. That was the same cost to us as having the original 2 small workers, yet we got 6 times the I/O, right? And that allowed us to keep up with how long it took and have enough instances to process the data at the exact same cost as having 2 small instances. So how do we identify bottlenecks in the system? This is, we said this when we were evangelists, and it's true today. Instrumentation is key. Custom performance counters are really nice. However, simple timers that trace are just as good in some cases. We have, and I'll show an example, we just turn on a timer. How long does it take to process this command? If it's over a certain amount of time, we trace a warning. Then you can look through your logs later and say, warn, warn, warn. Oh, what kind of command was that? Why is it taking so long? You can go in and dig into the system, figure it out. And you really need to watch for trends over time. This is, again, a true story. So here is a view of our CPU usage over, I don't know, what is this, 8 hours, something like that? Does this look bad? I don't know, it looks reasonable to me. I mean, it's somewhere between 20 and 35% most of the time. Okay, great. That's 10 hours of data. Well, if you zoom out about 10 days, you find that this is where that occurred. Something's going on, right? And if you don't look at your data over time and trends, you'll never notice it. We were actually getting slower and slower and slower over 10 days. This allowed us quickly to figure out, we need to attach profiling. So we went into the dev environment, we attached profilers onto the box, we figured out where our code was actually getting bogged down. And it turned out to be a serialization issue. Can you tell where we fixed it? That's how we know we fixed it too, by the way. You can only prove that you fix it after you measure it. Okay. I'll let Wade explain why we have a P around here.
Well, we're going to get into the demo now, and we're doing a demo on, it's called Beer Me. So we're going to show a highly scalable beer me system. And the reason we chose this is Ryan and I both happen to be pretty big homebrewers. And so any excuse to do something related to beer we look for. So actually his system's the one on the upper right. He's got a brand new electric system, which makes me pretty jealous, pretty envious. I have a pretty manual, cumbersome, old school system that you see there on the left. Yeah. But we're about to jump into the demo, and it's a beer me demo. So,
and if you look at me, you can't tell that I like beer, right? Okay. So I'll also preface this by saying this demo, I mean, it's a little rough. We're not UI guys, but the amount of work we put into this, maybe 8 to 10 hours, tops, I would say. This is not a ton of work, and it's easy to do. All right, so let's go back. Flip. I'm going to show you my solution. I'm sure you guys have seen Visual Studio before. I won't go into too much detail on that. I'm going to point out what some of these projects are. So we have an engine here. We'll call it an engine. Really, all it contains is some strategies that we have for things like serialization, quarantines, what common names or what conventions we're using in the system, so on and so forth. And this project kind of gets copied around into different solutions when we want to spin up new engines. We also have contracts, and this is the thing that actually gets distributed to web clients, for instance. So we all agree on what the message format is going to be. Here's an example of a command where someone sends me a command to register a beer lover. They send their name and an ID in order to later identify them in the system. Okay. The domain itself, so we talk about, I'm not going to go into a lot of detail, but there's an idea of domain-driven models. And what we have in our system is we have this wrapped up into an aggregate called a beer lover. And basically, this has methods inside of it for creating a beer lover, right? It will register the beer lover with an event. For beering someone, which will raise an event that you've been beered. And if you've been beered more than 3 times, you've become a beer lover intermediate. It'll raise that event. 6, you'll go to advanced, so on. More than 12, you'll be a connoisseur. And there's some convention to this. It might look strange, but this is a convention where we're internally storing the state of this user in a class here that actually that contains the information itself. So what we do is when these events get raised, this aggregate replays the events in memory using these apply methods. So if we have a beer lover advanced, it sets the internal state of this beer lover as advanced. When you're registered, it sets the internal state of the beer lover, their name, and what type of user they are, right? This looks a little funny, I'll admit, but we found in practice that this scales like crazy. There's also some very nice benefits to this. Okay, so I'm just going to show you what this looks like running. So I start this, and this is just the engine, right? So this is the event dispatchers, this is the commands, and I'll show you how they're wired together. First, let me show you how it works, and then, did I screw something up? Okay, I must have hit a button somewhere. Hang on. Build succeeded. Let's try that again. I'm going to show you how to use this inside of, what is going on? I don't see an error list. Would you believe this works? Luckily, I have this running in the cloud, so let's just go to the cloud. All right, so here's how you would use it. This is a client. Remember, you have an engine running, and the engine is listening for messages that are coming in. They'll be dispatched to the command handlers. We are simply using a a convention here, a tool called LOCAD CQRS that actually wraps a few concepts for us. It does things like it understands how to interact with Windows Azure queues. It knows how to apply serialization. It knows how to do retries, for instance. So this plumbing really is kind of built into our framework. We don't have to worry about that as much. What we really have to worry about is simply what commands we're going to send into the system and what gets generated. And I'm really disappointed that this is not starting up. Let's just run the last emulator. All right, let's give it a shot here. So I'm going to send a command into this engine, and then I'm going to immediately come back and query a repository for a view. I'm going to do this instantly, right? So when I do that, I get nothing. So I asked for a beer lover profile, which is a view that I have in the system, and I get absolutely nothing. However, if I run this again, if enough time has passed, you'll see that suddenly I get the view. Remember I said you have to learn to be okay with stale data. The message is dispatched, command handlers handle it, they raise an event, denormalizers pick it up, denormalizers write the view. This is an asynchronous process. So you have to be okay that the data is going to be stale. And we found that we are okay with the data is going to be stale. I mean, the user could have been sitting on the screen for 30 minutes. We don't know how long a particular thing is going to occur, but we found that, 5 minutes, it's okay. No one's bothered by the fact that your data is not instantly up to date. If you do need it to be instantly up to date, you have to put a little spinner on the screen. Say, wait. Okay, now it's ready. All right, so I've pulled back a view, and let me show you what that was. So inside of here, in my dev storage account, I have a blob container with views, and you'll see I have a beer lover profile, and it's just sitting out on disk. If I open this up, it's just a JSON file. So this is the only thing that I have in the system right now. Now, if I come back and I send another command into the system, this time I'm going to actually send a beer me. If I come back to this view, you'll see it's been processed in here. First chance exception, hopefully. Refresh. Beers consumed 1. Unique styles IPA. Imperial IPA, actually. But it came through and it updated the view. Now, simultaneously, what we've done is we've registered these denormalizers, and we have 2 of them. This is the one that actually did the work. I'm going to shut down and let you get a look at this. We simply listen for when beer lover is registered. It will actually come create a class called beer lover profile and write it into our storage solution. Similarly, when you've been beard has been raised, which happens after you beer someone, that event got raised, then we just simply go in and update the unique styles and add our beer into consumed. Now you look at this and you say, well, okay, that's maybe good, maybe not. What we get, though, is we have a history of the events in the system. So let me show you what my local machine looks like. I'm going to grab my local machine. I'm going to select out the commits. And all we've done here, and unfortunately I can't zoom in too much on this, all we've done here is serialize this data into our database locally as an event. This now has 2 purposes. One, we have an audit history of everything that has happened in the system. So when you're running a service and a user comes to you and says, my system's out of whack, I'm missing X, you can look through their history and go, well, yeah, because I can see that you deleted it right here. I have a command, or I have an event that was raised from you that you wanted this thing deleted at this point in time. If you don't use a system like this, you're going to have to either roll your own, or you're just going to see the end state, and you won't know why it got to that. The other big benefit to this is we can change the view at any time. and regenerate it as if it had existed for all time. So an example of that, we're going to replay the events, right? So let's talk about what I'm going to do here. In the profile view handler, let's just assume that I don't really want the not bad you've tried more than adjunct loggers or the noob. Where's the noob? Not bad, keep trying. Let's do good job. Unfortunately, this won't build right now, probably. But if I want to do this build, anybody know this error? That is crazy. Okay. Yeah. So what I can do is I can simply go back and I can replay these errors. So here is, I'm just grabbing our storage connection for our senders, and I'm wiring into the event store. This happens to be the dialect for the event store. And then I'm grabbing every commit, opening them up, and simply dumping them back into the queue again. So I'm replaying the messages over and over. Now imagine I've rebuilt the view. I've changed how the view should operate. I'm dumping the same messages through the system. What it does is it regenerates the view. Now imagine I add a new view. I can replay all the events for all time and create a brand new view as if that view had always existed in the system. So we found that this behavior has allowed us to add new features very easily, create new views, and create one-time views for different specific purposes without ever having to remember at the very beginning of design, this is how that screen should operate, right? We get to the screen, we look at it and we say, well, it would be better if we had this data. How do we get that data? Oh, we'll just add it into the field and we'll rerun all the events. Done, we have all the data. And now it works. It's apparently restarting Visual Studio. It's like Windows. Okay. So I've spent a lot of time on this particular demo. I want to give Wade some time as well. He's got some more demo on here, and I'm going to leave it at that. Wade.
Great. Thanks. So Ryan's made a couple of points today. That what I want to do is reinforce by showing a separate demo. So Ryan just showed you the engine that processes and builds a lot of these views. Well, I want to show how you'd actually go about building an API, a lightweight API, and start interacting with this data. Because one of his points was we scale the back end quite a bit, but we usually don't have to scale the front end. So I want to show how we build web APIs to interact with the system. And the other point I wanted to highlight in doing this is because of this model, and because of the fact that it's disconnected, we can work on these APIs completely independently of someone like Ryan who's going to be working on the back end. And so it does allow our development teams to focus on things that they're good at and work in parallel. So what we have here is a web API project, and as long as it has the ability to know how to serialize to the views and to the aggregates that the underlying system has, it works completely fine. So we have a couple of different things here. We have a web API controller that will do a register event. So Ryan was showing you a link statement earlier that showed how you could go and register a new user. Well, what we have here is a web API that allows us to make a post and to post in our beer lover model and actually call that register beer lover event and send it. So we can actually then create and then return a response code that's appropriate back to the user, telling them about the beer lover that was just created. And so what I want to do is, this runs locally. We've also deployed this up into Windows Azure. So if you take a look here, we've got this running in a web, on a Windows Azure website, which is another point that's important since since all this application does is really just manage the posts back and forth between the systems. It can be pretty lightweight and allows us to use a lot of the nice tools that come with Windows Azure websites, so we can do Git deploys and so forth directly to it. So this system's up and running. I'm going to use another tool here called Postman. That's a great way to actually just manage and work with your HTTP requests. So the first operation we're going to call is register, and you can see here that it's pointing to our website, and then it's just calling into the register API. And what I'm going to do is pass in a name. I see Nuno up here front, so I'm going to go ahead and create and register a user here for Nuno. I'm going to send that command, and you can see that I get a response back, and it's the model that comes back to me. And in addition to showing that it's been created and I get a response code that's 200 OK, I also end up getting an ID now that I can use to refer to Nuno. So I can grab this ID, and then we have another controller here called BeerMe. And all BeerMe does is it's got a post here where I can now send that ID along with the type of beer that Nuno likes to drink. And I can beer Nuno. So basically, I'm going to take Nuno's ID, and let's see. I'm pretty sure I saw him drinking an Abita last night, so I'll go ahead and beer him. And you can see I've gone and beered him, and that has been registered. So it's in the system. Presumably, if I don't know what link statements or what Ryan has up in LinkPad, but even using LinkPad, we could go in and actually query and at some point see the aggregates that were created. We've created another web API that we could use to go ahead and get information about the beers that a user has consumed. So here, we've got a user beers API that we can call and take a look and see all the underlying beers that a user has consumed. Now, the thing is, I've issued one command to beer Nuno, but it's actually created two different views. I don't know that Ryan actually demonstrated one of the views. He's actually writing each one of the BeerMe events to Windows Azure tables, in addition to an aggregate that's being put in blobs. So that's one of the nice things about this system is you can have multiple views created off of the same commands. So this command here, when I do a get, will actually show me everything that I've actually logged for Nuno, and not just the aggregate view that's been created by the system. So if I come over here and say, BeerMe, and I pass along the GUID that represents Nuno, Here, I lost it. So I'm going to go ahead and call this here. Let's grab the GUID for Nuno. I'll paste this again. And send. You'll see now that when I do a post here, I'm going to end up getting back this aggregate that represents Nuno. So it's going to give me the unique styles that he's consumed. So if I come back here to BeerMe, I could also include, how about a Pliny the Elder? And then if I come back and run this again, you'll see that here's also Pliny the Elder associated with it. Did I get the right ID?
No.
I didn't, did I? Okay, here I've sent the command for it. Now let me update this. And then eventually it should come back and show us.
I think you accidentally pasted the wrong.
Did I paste the wrong beer
That's
lover
okay.
ID? Okay, well, apologies. But the idea is that as it's going back and forth, you'll see that this. Wondering why I did that. But anyway, we can send additional BeerMe commands, and the aggregates end up getting created. And so here we can also take a look then at all the different beer lovers that are in the system and who they are. Now this returns a view then of one of our other views, which is the table store. So all of this information then can be used just through any kind of client that can now speak HTTP, leveraging these API controllers, which in turn are able to work with the underlying engine to send the commands and then end up querying this data back.
So we end up using this a lot in terms of how we split our workloads. Wade mentioned we have different teams. Well, our different teams also have different capabilities. Obviously, our web developers are quite good at developing in the web tier, but they really have no idea the back end's working. When you can tell them, hey, look, here's a JSON file. I'm going to create a view that kind of looks like this. Just bind this data to the front end. Don't worry about how you get it, really, because I'll wire that up for you. But buying this JSON view to the front end, it accelerates development tremendously. They will take a model, a sample of what the view is going to look like. They can do all of the work. They can wire it all together using that sample data. Then you come back and you wire in the implementation. The implementation just says, go to Windows Azure, pull the blob that is this ID, and that is exactly the data that they bound with. So you actually can accelerate your development that way very easily.
There we go. So yeah, I think it was a GUID issue where when I actually sent the command, I didn't have the dashes in it, and it still wasn't doing the right conversion. So resent it, and now you can see that the engine did pick it up, and here is Pliny that's been added. So we were able to beer Nuno. So
awesome.
Thank you for your participation, Nuno.
All right. So the big technologies that you actually saw in use today that we found have worked very well, REST APIs. Our scheduling engine today in the store is completely web API based. So we have a portal that has nothing to do with scheduler at all. It completely communicates via what an example like web, what Wade showed here. It completely communicates via just AJAX commands into an engine, and then it reads static views back. It's not even in the same solution. It's completely different source code. We just told our developers, here's the name of a command you send, and here's where you go to get the views. It runs on 2 instances. It barely sweats. I mean, it doesn't have to do much, right? We found that Locat CQRS, as an example, worked very well for us. This took care of a lot of the plumbing that you saw, how queues work, the retry policies, so on and so forth. As well, you saw the J. Oliver event store. So that's what actually takes that serialized event data and actually puts it into, in our case, we're using just SQL, but it just stores it as basic binary blobs inside of your data set. With these 3 technologies together, you can build some pretty highly scalable systems. What we found didn't work real well. We actually had a lot of trouble with WCF. And this is not a knock on the WCF team. I'm sure they get it all the time. But we found that we couldn't properly configure it. There were too many knobs in there. We actually got bit by customers. We were calling Service Management API, which used WCF contracts. And some customers had very, very long descriptors inside of their service management call. And, well, WCF has a maximum message length buffer thing, right, that you would never deal with if you just use HTTP, but WCF has, and it would actually blow up the system. So we ended up having to spend a lot of time troubleshooting, tweaking WCF, when if we would have just used a simple HTTP client to download the XML from the Service Management API, it would have saved us a lot of grief. Binary serialization formats. Not only, we used to notice everything we used was JSON. It's high performant enough for everything but pure binary data. Trust me, it works just fine. The big reason we use that as well is we can inspect it at rest and see what's in there. If we need to, we can encrypt it, but we can inspect it at rest. When we used a binary serialization format, we got into trouble later because we'd tweak a contract, right? So the command would have today name and ID, then later we wanted to put state. Well, that would completely blow up because the binary serialization had been stored inside the database with a certain contract, and it was unforgiving. If you change it to JSON, you actually can get away with murder on shifting these types back and forth or having serialized upgraders that are upgrading serializers that will add the necessary fields. Entity framework. I'm just throwing this in there because we found that it's a lot more trouble than it's worth in our opinion. If you look at how we built the system, viewing JSON files, there's no database in here at all, right? We're querying table storage, and the extent of the query is really return top 220 rows, top X rows. And that's pretty much the extent of the query. We don't need joins anymore. We don't need lookup tables because we pre-generate those in all of our views. The only thing we ever have to do is go find the file and display it exactly as it is. We found in the entity framework, when we tried using that, we ended up changing the schema on the database, which then caused upgraders to get registered to upgrade it because we used the code first. And we had synchronization issues, and then you just have to deal with having an actual database there. And it's really not necessary. I know, probably crazy view coming from someone who used to work at Microsoft, telling you that entity framework, probably not your first choice for a really scalable system. I know the entity framework team is going to shoot me later. All right. I wanted to touch on a couple more topics with our remaining time and show you how we do these things. So automation. Automation. We have build automation, deployment automation, and we have automated data migrations. So when you change data schemas between versions, we actually have a process in place to actually automatically upgrade the data as it goes along as well. That's one thing Entity Framework does a pretty good job of. We use something that's very similar. So why do we do it? Obviously, reproducibility. We're a small team. It takes the I forgot out of it. And finally, if we don't have this, there's no way we can ever intend to take the same deployment and put it in any other data center in the exact same fashion. So we'll deploy to multiple data centers. And remembering to set the connection strings every time correctly, remembering to configure everything correctly each time, you're going to make a mistake. Visual Studio is not a deployment option. It's strictly forbidden for us to deploy from Visual Studio, except on a lark, never to production, but maybe to a very special dev cluster because you want to RDP into it to look at something. You would never use it. We have continuous builds, so every check-in causes a build to occur with unit tests to be run, and these data migrations I talked about that are automated tie it all together. I'll show you a little bit what this looks like. So with very small effort, maybe, I don't know, an hour, I actually launched an IaaS machine, which I finally found a really good use for IaaS in Windows Azure. No, I'm just kidding. I launched an IaaS machine, installed TeamCity, and created 2 build profiles. So this is actually how we deployed the Beer Me demo. One of them is a debug build profile, and in this configuration settings, we just have a step that actually builds the solution. And there's a trigger that listens to our Git repository, and every time it sees a push into the Git repository, it causes a build. Now, normally there would be another step in here called run unit tests, but you notice I don't have any unit tests, so I don't have this step in here. Bad Ryan, I know. The other build configuration is actually a build and deploy. Now, it has a couple other steps. It builds, and then it calls out to PowerShell. So we use the Windows Azure PowerShell commandlets, and we can take the generated package and simply pass it along here in the command line and actually deploy that into any slot or subscription or hosted service we want. So you imagine this runs daily, so every night, midnight, we have a build that goes out. We can always go to the latest build we know is running on a server every day. And then on commands, we can also run this at any point in time simply by hitting this run button. This will actually go pull the latest code, compile it, and do a deployment. You walk away, eat a sandwich for a little bit, and you're done.
One of the things we've also done in our environments, not in the demo environment, is on our dev test environments do a continuous integration as well and a continuous deploy. So when we do a check-in, it doesn't just do a build and then run unit tests, but it'll deploy it to our dev test environment.
Yeah. We don't do that in production. You'll see a different profile in here for production that has a very exclusive run button, right? And we usually use different branches. So we have master as our dev tests, and then we have a production branch, and we just merge over to production. And then this build profile will pick up when there's something sitting in the production branch, tell us it's ready to be deployed. We'll have it tested. We'll hit run, and we'll deploy the entire environment. All automated. So we don't have to do anything. The other part of this is in our environment, after the build deploys, the first role starts up and checks to see if it needs to do data migrations. So then it'll go do the data migrations before it really fully comes online. And that prevents us from having issues and reproducibility problems. Okay. Now, we talk a little bit about deployment patterns, kind of best practices of what we learned in doing this. So a little bit about PaaS versus IaaS, extra small VMs, websites versus web roles, whether or not you should have one deployment or many deployments. Now, there's more than one way to, is it punch a cat, skin a cat, slap a cat? So I wouldn't take this as prescriptive, but as this is our opinion, it's worked well for us. Your environment or your needs might vary, so you can just listen to this as an experience and not necessarily as you must do. So for our environment and the way we have our architecture set up, no one is special. All of our roles are the same. We can shoot one, we can grab more. The overhead of building an IaaS image and maintaining it is just not worth it. I don't want to patch it. I don't want to deal with any of it, right? I just want that engine to run. I want the website to run. I don't care about that machine. We exclusively choose PaaS, always. The only exception to that is the build server you saw. That's it, actually. We, at one point in time, tried using an event store that wrote to disk. And because of it wrote to disk, we had to actually use an IaaS role as well because that has persistent blob back storage, right? However, we found that we weren't getting the IOPS that we really needed in order for it to write through to the disk. We had some problems there. So we ended up actually ditching that solution and going back to the J. Oliver event store. Luckily, that's an easy transition to shift between different event stores. It's pretty much all abstracted. So that wasn't a big deal. But that is the only time we've ever used IaaS. Now, I'm not saying that that's always going to be the right solution for everyone. You might have stateful services running somewhere, or you might be more comfortable RDPing into the box or using remote PowerShell to install something like a driver or something after the fact. You might be running SharePoint in the cloud or AD, and you need these integrations. IaaS is absolutely the right choice. For run-of-the-mill large-scale services, it's not. It just isn't. PaaS is a much better model. You won't be led wrong on that. The next point here is around extra small VMs. We really used extra small VMs, and they are well worth their money. They have limited bandwidth, but if you can live within that constraint of memory and bandwidth, they're worth their weight in gold. Right now, the price has gone down a little bit on the small roll. I think it's like 9 cents now or something. But at the time, it was 12 cents. An extra small was 2 cents. If you can split up your work enough, you can get 6 extra smalls for the price you were paying for one small. Huge bang for the buck. We used those because we needed something that would wait out a long, potentially drawn-out network operation. Well, you can throw a ton of extra smalls into that solution, work on that. That takes a really long I/O. It doesn't take a lot of memory, all those things, but it takes a really long I/O. You get much better performance across your system. Finally, Azure websites versus web roles. I think I have a slide on this. So the Git deployment on Azure websites is very nice. This is where you hear me say, but the ability to use the role entry point on the web role is often more important than Git deployment. So we use this a ton, right? We can run background processes. We're going to use our hardware, right? It doesn't have to just serve web. It can actually serve other things as well. We might have multiple servers. We might have multiple sites. We use web roles a lot. Now, we also get to control the dependencies on the machine. Right? We can install agents. We can install drivers that you frankly can't do in websites today. We can scale beyond what websites allows. And finally, the SSL support on those is free, which is a big deal, right? They just released SSL support. However, if you look at the cost comparison of what it costs to have SSL versus just running it yourself in a web role, you really should do that math because it's probably pretty close, right? But Git deployment into Azure websites is nice. I want to reiterate that. That is nice. All right, single versus many deployments. When we were evangelizing, we always said, look, take everything, put it in this huge service model, and then deploy it, right? You have 10 roles, 15 roles, and you have a worker role here, you have this there, you have that there. In practice, we've started to actually change that up a little bit. And the reason is, it turns out your roles are often upgraded at different times and different life cycles. So in theory, it sounds really good to have our scheduling engine tied to the front end, for instance, that serves. And sometimes there is a little bit, like the contract for the messages has to be coordinated, right? But most of the time, it's not. We're making constant improvements to the back end. There's no reason for us to redeploy the front end at all. So we've actually found splitting these up into different deployments has been a big benefit. Now, obviously, when you geolocate something, you have to split it up anyways. But within a service itself, all the components itself, the roles, take what you think is really your unit of upgrade, where if I upgrade this, I got to upgrade that. That should be what you deploy. So good candidates for splitting out are a lot of times going to be web from back end. You're going to upgrade and you're going to actually deploy these things separately. How do you handle different upgrades when you are in geodomains? For us, we had a routing capability within the message. In fact, I can show you kind of what this looks like. But when we dispatch a message, I'll show you it here. When we dispatch a message, we have a routing function. So we have a handler that sits on an inbox for a router queue, and it calls this function. It simply comes in, and this is an example. This is very simplified, but it can be much more complex. And it says, look, take the message that comes in, inspect it if it's an event or if it's a command. And if it is a command, this is where we could really plug in for geo-routing. We could say, well, what kind of command is this? And who's it for? Where should this really go? So we send our messages into a common inbox. The inbox gets popped, and then we look at it and we say, where does this really need to go? During our upgrade strategies for geo, right, we had different websites, or sorry, different worker roles going down. What we would do is we'd go into our configuration and just say, North Europe is offline. All the messages that should have gone to North Europe would get rerouted to the US while North Europe came down, if it was important, right? If it wasn't important, we just sent it to North Europe. It got queued anyways, and when North Europe came online, then it would just process everything. So we use that strategy. Or it might be you want something in like Singapore, but you find out it's really expensive because of bandwidth or whatever it is. You can turn off routing for certain parts of the day or however you want to do it. The last thing I should put in here, I forgot to mention, I mentioned but I forgot to show, is here's an example of how we can still instrument within our code without spending a lot of time on custom performance counters and setup and maintenance and those kind of things. This is how we're actually doing it. So a message gets dispatched, this method gets called, and we will simply start a timer. Actually do the work here on the invoke. And this is doing it's doing a little reflection magic to figure out where to route that message, which handler has it. But once it's invoked and finished, we stop the stopwatch. If it's more than 10 seconds, we write out a warning. And then we'll actually be able to instrument our system. Okay. And finally, let's talk about handling outages and disaster. So we were in Windows Azure when the last two big outages occurred. I don't know if you guys remember this, but there was a leap year problem. You remember that one? So we were actually running our service at that time. And all I can say to you is that outages are very, very common. When you run a service that monitors Windows Azure and you have thousands of VMs, you will see outages regularly. It could be for 5 minutes that storage is not available. It could be for 5 minutes the SQL Azure is going through an upgrade and the database isn't flipped, or whatever it is. Or your role becomes just unresponsive. That's happened a lot as well. But you will see it. And so you have to plan always. And the way we take a look at this from Aditi's perspective is the type of load. We do an analysis. We say, look, how important is this? Right? A scheduling service that's doing webhooks, yeah, kind of important, but maybe not that important. An eventing service that's used for emergency notification, yeah, pretty important. We can't have outages. So we'll look at strategies within this that just say, look, are we going to take this and deploy it into multiple data centers? Are we going to deploy it into multiple clouds? One of the things we learned, right, is if you're writing monitoring software for Windows Azure, you probably want to write the monitoring software for Windows Azure not in Windows Azure. If Windows Azure is down, so is your monitoring software. And that happened, right? Storage was out. The SSL cert was wrong. However, if you had a dependency at all on Windows Azure, you were down. So we found this out the hard way, and we figured out where we need to place our assets. So we're primarily Windows Azure users. We wouldn't be here otherwise. But we've also found that it's not uncommon, and it's not, I don't want to say, but it's not, it is a good idea to also hedge your bets and have a plan in place depending on the type of service you have in order to how to either spin it up in Amazon or Google or whoever or on premises, but have a backup plan depending on what it is. And remember that the best you can do is the multiplication of each SLA. So you might be up 99.95 on your web role, but storage is 99.9, and SQL Azure is 99.9. And if you're using all of them, you're really up only 99.75. That's the hard truth. We talked about this a bit. We really weighed our risk, and we took a look at what can we absolutely do. Could we synchronize data between data centers? Should we move this? Should we take periodic backups? What's our time to recovery? How bad would it be if we were down? And we found that, hey, you know what? If we take daily backups of our database, our event store, we can actually move that to another cloud or another data center within 4 hours. And we decided, we probably don't need an always-on, always synchronizing copy of the data running, because we felt pretty good about being able to bring it online quickly. Now we have another project that is much more important. It's around emergency notifications. And we're taking extreme steps in that case, running in multiple clouds in order to make sure that that environment is always available. Okay. So we've covered a lot, and I realize the CQRS demo was for non-technical people might be a little deep. The nuts and bolts of this, though, is when you're building for scale, you choose the set of technologies, obviously, that's going to give you the best performance, the lowest cost of investment, so on and so forth. We shared today some of what those tools were for us, and the patterns we found work extremely well in the cloud. That happens to be CQRS. You can use different frameworks than us, but it happens to be the ones that we chose today. And those strategies push your hard work to the queues, optimize for your reads always, split your read and writes, learn to live with latency in your data. Those will build you scalable systems. We can prove that. DevOps side, automate everything. When we're a small team, automation is key. You're not going to be able to reproduce it every time, and if you have a person whose job is build manager, you're probably doing it wrong. If that's the person who has to go in and change the connection string on every machine after they deploy, right? Handling downtime and disaster. What can we say? It's going to happen. Have a strategy in place. With that, we have about 5 minutes left. If anyone has any questions, want to come up and inspect the code a little bit more, we'll make all of this code available as a sample. We'll publish a repository, so look for it on the event site. If not, look for our blogs. We'll put it up and tweet it. Wade here has like 2.5 million followers, so you'll find it out there. If you do have a question, come up to the microphone, please.
Hi, I had a question about the connection strings.
Mm-hmm.
How do you, so we store all the connection strings in the database, but there's one connection string to connect to the database that we have still in our code, and it's different for different environments. So how do you tackle that problem? And then the problem is that your dev config has the connection string for the dev environment. When you move it to the QA environment, you need to just change the connection string and some other configuration information. How do you manage that for automated deployment?
We have different build profiles. So if you look at the, I mean, the answer is simple. In some cases, more complicated. So depending on what it is, right, we actually have build profiles in here. This one's only using cloud and local. But when you deploy, you specify which build profile you're deploying, and it'll actually put the right settings. Now, some settings cannot be stored in here, and they have to, for instance, be in web config. In that case, you can actually just use, I'm sorry, I don't have a web role in here, but you can actually use the debug release profile kind of behavior that's just built into Visual Studio.
Yep.
And also, one of the things we've also done is if you have to put it in web config, oftentimes you can ignore that, and then at runtime in your global ASAX or something like that, actually read files out of the service configuration file and then load things up at runtime to get the settings that you need versus putting them into web.config. So like for for ACS, when you're doing like your system.identity, a lot of that stuff typically is put in config, but you can load that up in runtime and extract from your configuration file instead of kind of hard coding it in your web.config.
Okay. Yeah, the problem that I run into basically is we deploy across multiple domains, and our domains are not trusted with each other. So, and then we have like just like you have right here, but we have like many such configuration files, and it starts to spits out all these builds, but we ultimately land up with a lot of problems with them. I like this second suggestion that you said something about using the other file. I'll step up over there and maybe talk to you.
Great.
Okay.
All right.
Well, thank you.